Okay, Jim Frankenfield here with another video on factoring. I have a previous long video on factoring polynomials and focusing mostly on rational roots. There were a couple in there that had irrational roots we could deduce, and we came up once or twice with imaginary roots. Today I'm going to do a problem that came up on help group, this polynomial has some irrational roots. We're going to start out using the same methods, but it's going to require some additional, more advanced methods to find all of the roots. So this is the polynomial we want to work with. It's a fifth order, so we want 5 roots. And we'll start by seeing what Descartes' rule tells us. We have 1, 2, 3 sign changes. So we're expecting 3 positive roots and 2 negative roots. Sometimes that turns out to be helpful later, and sometimes it won't. And we know that any rational factors of this thing need to be factors of 210. And I'm going to go to my spreadsheet method because there's going to be a lot of factors. But we need to find all of the factors. We need to start by finding the prime factors. So divide by 2, we get 105. That divides by 3, which gives me 35. That divides by 5. So I have 4 factors. And I'm going to have a total of 2 to the 4th, or 16 combinations or positive numbers from this, and I'm going to have the negative numbers as well. So I'm going to have 32 possible factors of 210. Now, if I wasn't using a spreadsheet, I'd start with the positive ones because there's a slightly higher chance of finding a positive one, and I'd also start with the smaller one. What I'm going to do here now is switch to Excel and use my spreadsheet method here. Okay, so let's take a look at the spreadsheet. What I've done is put the prime factors up here at the top, and I want all combinations of these. So I'm going to start filling this in the way I would fill a spreadsheet. I'm going to speed this up. If you're not familiar with this or you can't see what I'm doing, go back to my previous video. Okay, so here I have all 16 combinations of prime factors. Each one of those will give me a different factor. So I'm going to have to multiply these here. And I'm going to just multiply each one across. And I'm just going to do that for each of these, and I'm going to have all of my factors. I also need to use the negative number for each factor. So this is just equal to the opposite of this. And then for each factor, I'm going to calculate the actual function. So this is the value of the function for that factor of 210. And I'm going to do that for every factor. And now I'm going to look for the zeros, and I have a 0 here. So make that one red, and I have a 0 here. These are our 2 factors. I would say my 2 factors, but there's going to be 3 more factors. And they didn't turn up as rational factors. So this method has reached its limit here. But we have factors of a -6 and 35. So we have two factors now, and that means we have two roots. Our factors would be x plus 6 and x minus 35. And that leaves three more that we don't know. What we're going to have to do here is find the remaining polynomial, and that turns out to be x cubed minus 3x plus 1. Okay, we want to find the roots of this factor. You're going to have to find this by dividing the original one by the two that we now know. After you divide those out, you'll have this function remaining, and this has three roots remaining. We found one positive and one negative, so we have two positive and one negative left. So let's see how we can find those. There's going to be two ways to do this. The first one doesn't really require calculus, and it's a brute force method. We just zero in on it. And the second one is a little more eloquent and requires a little basic calculus. So the first thing I'm doing, this final polynomial doesn't have any large factors, so it's going to assume all the action is somewhere close to 0. So I'm going to try values from -5 to 5, and I'm just going to calculate this function, which I'm calling g of x. It's not our original function f now. It's a factor of that. So I can see that I have three places here where it changes sign. Between -2 and -1, between 0 and 1, and between 1 and 2. And I can see that just from calculating this on the spreadsheet. You could do this on a graph. You can go to, I'll look at this on Desmos later. I would show you these ranges. So let's go back here and let's look for the one between 1 and 2. Let's try to find out what that is. So we're going to go from 1 and we're going to add it. We're going to look for the first decimal place right now. So I'm going to drag this down. This goes from 1 to 2, and this is the value of the function. And it changes sign between 1.5 and 1.6. So 1.5, and let's do this again. We'll do 1.5, and we're going to add a new decimal place, 1.50, 1.51. And I'm going to drag these down here, and it changes sign here at 1.53. So now I have 1.53. And I'm going to do 1.53, 1.531. And the next one is going to be 1.532. Okay, so I'll just finish doing this a bit more. Okay, so I did that a few more times, and I found that I have 1.53208. You can go as long as you want on this, depending how much accuracy and precision you want. And that's one of the other two roots. And we could do this for the two other ranges, between -2 and -1, and 0 and 1, and you would have the other two roots. But there is another method, and once we set it up, this will be quicker and easier. Let's go back to okay, so let's go back here, and this is called Newton's method, and this involves a little bit of calculus. If you want to know more about how it works, it's explained in many basic calculus books, introductory calculus. So it's an iterative method. So your nth approximation is equal to your last approximation minus the function at that value divided by the derivative of the function at that value. So we need the derivative of this function, and that is just 3x squared minus 3. And we can do this on the spreadsheet now too. So we have on the spreadsheet here, we are going to have these are my iterations. This is going to be my first value, and then I'm going to calculate my subsequent values, and the longer I do this, the more accurate I will get. Over here, I'm going to need the function of my previous one and the derivative of the previous one. So here I calculate those things. And I have to choose a starting value, which here is 2. So now the next value is based on the previous one. So this is h2, this is the previous value, minus I2 over j2, this is minus g over g prime. And this gives me my next estimate. This will be closer to one of the roots. And then I calculate g and g prime, which I need for the next step. And I just keep repeating this. And here I am at 1.53208. That's the same root that I found last time. This time it's much easier to go on and find the other ones. We started with 2. Let's see, we had, let's just try -1, see what happens. Well, okay, sometimes you end up with an error. This is going to be because your derivative is 0 at this point. So let's try -2. And here we get another root. So we have minus 1.87939. And let's see, we had, we're looking for another positive one. So let's try another positive number. Let's try starting with 1, which I got 0. Let's try starting with 3. Let's try starting with 0. Okay, here's another positive root. So I have 1.53208 minus 1.87939. And you can just try different starting values. If you try something that's not close, it should still be zeroing in. This would be my 1.532, but it still hasn't gotten there. I would have to extend this down and do more iterations. And down here, I do get the same root result. So that's how we can find this. Let's take a quick look at it on Desmos. Okay, here's the graph on Desmos. You can see, and this is only a graph of g of x, the cubic, okay, not the original function. But here's my negative root, positive root of 0.347. Here's one of 1.87. So these are the roots. So you could look at this on Desmos first, and you can use it to find the answer, or you can use it to find your good starting points. So a good starting point for Newton's method might be 2. If I'm doing it by the brute force method, I might want to go between 1 and 2. So I could start out on the graph. So let's go back and, okay, so here's my original function, and I have factors, okay, so I have x minus 35, x plus 6, x cubed minus 3x plus 1, equals 0. These would be my factors. And actually, the only answer that's got in the help group was to factor it, and you just stop there and say you can't do anymore, which, if you're factoring it, is true. The question was to find the roots, and nobody pursued that. And it is a more difficult problem. It's not as simple as your common rational root problems. So we do have 5 roots. We expected 5 roots from the 5th order, and we expected 3 plus and 2 minus. So we have a 35, and we have a minus 6, and we have a 0.347, and a 1.532, and a minus 1.879. So here are 3 positive roots and our 2 negative roots. So Descartes' rule still works. It still tells us how many plus and how many minus. We can start out the same way we do with rational roots. If you don't like the spreadsheet, you can just start finding factors and trying them out. And that's kind of the old school method before Excel became so powerful. But Excel is just a tool that helps us try out all of these factors. And we found 2 of the factors are rational, and they showed up on the spreadsheet method after trying absolutely all of the 32 possibilities, which is easy on the spreadsheet, not so easy without it. And then we found that we had to divide and see what was left, and we have 3 more roots, and we had to use some more powerful methods on that. So if you don't know anything about calculus, you can use the first method, zero in on the roots. If you do know a little bit of calculus, you can use Newton's method. There are, as usual, some ins and outs to Newton's method. It works pretty well most of the time. It worked well here. You can see that if you get a 0 derivative, it blows up and stops working. There may be a few other limitations that I can't recall offhand. So if you're going to rely on it too much or it doesn't seem to be working, you need to go get out the basic calculus book. But or you can go back to the other method. So that's how to do one with rational roots. As I'm doing now with spreadsheets, I'll put this on my website, jamesfrankenfield.com. It'll be in the academic library area. And so if you want to see the actual spreadsheet, of course I sped up through some things, and that's not going to be repeated there. But the form of the spreadsheet will be available if you want to play around with it with another function or use it for something else or just see what it was I was doing. It'll be available there. So that's it, and I hope that's helpful when you run into a more challenging factoring problem like this. It can be, you can find the roots, not only the factors, you can find all the roots. It just is not as simple. Okay, that's it. Bye.